Hello, and once again, welcome to another series of lectures in the main heading Organic Reaction Mechanism. And before you watch these videos, you must be very familiar with general concepts in organic chemistry, what I used to call GCOC. We have 12 videos on GCOC, starting from the different types of cleavages, bond cleavages, homolysis, heterolysis, to electrophiles, nucleophiles, free radicals, and reactive species like carbocations, carbanions, nitrines, free radicals, carbenes, and their formation, their relative stabilities, and different electronic effects, namely I effect, that is inductive, resonance effect, hyperconjugation effect. And we have also seen the versatile applications of these I, R, and H effects in studying the relative stability, acid strength, base strength, bond length, bond order, and all that. So you must revise before you watch this series of lectures pertaining to reaction mechanism. As you know, a mechanism is the pathway through which a particular reaction proceeds. Is it a single step process or a multiple consecutive reaction? And what are the different intermediates formed? And what is the order of reaction? First order, second order, and all that. Today, we will be confining our focus on the substitution of alkanes, or we can call substitution in sp3 hybrid carbon, with a special reference to halogenation. And those who have studied the chemistry of alkanes, that is the first chapter in class 11, will definitely get immense benefit. And of course, those who are revising, they also will be benefited. So now see this, I am just trying to read out the simple things. Just read with me. Hydrocarbons having sp3 hybridized carbon-hydrogen bond often undergo substitution, such as halogenation, vapor phase nitration, sulfonation, and the like, by free radical mechanism. That involves free radicals. You know what are free radicals? Any species having an unpaired electron. They are neutral, but very, very short-lived, unstable. Now, look once again. Alkenes having allylic hydrogen. Arenes having benzylic hydrogen undergo free radical halogenation easily in presence of light, that is UV or visible radiation, or heat, or both. Now let us confine to halogenation of alkanes. That is the easiest to understand the mechanism, how free radical process occurs during halogenation of alkenes. We can extend the same concept to alkenes having allylic hydrogen and arenes having benzylic hydrogens. Hold on. Now, in a simplified way, we can say that in gas phase halogenation, alkane and halogen, that halogen should be either chlorine or bromine. I'll tell you why we forget about fluorine and iodine. I'll tell you. Hold on. In the presence of light or heat or both, hydrogen atom will be substituted by halogen, chlorine or bromine. to give you alkyl fluoride or alkyl bromide, and HX is the other product. This is the halogenation, and that is substitution. And the name of the substitution is free radical substitution. Just let us follow step by step. And halogenation order is like this. Fluorination is fastest. It is dangerously explosive. So we don't recommend to carry out fluorination. Even in dark, it explodes. So this is rejected on that ground. Chlorination is much faster than bromination. And iodination is still much less slower. So we neglect this due to its thermodynamic improbability, as we shall consider after some time. This is neglected, abandoned because of its aggressive, explosive nature of the reaction. So we concentrate on this, chlorination and bromination. Now what happens in this process? A carbon-hydrogen bond breaks, a halogen-halogen bond breaks, and in turn a carbon-halogen bond is formed and hydrogen-halogen bond is formed. So this bond breaking and bond making, the sum of these processes is exothermic, excepting iodination. In iodination, the overall process is endothermic, but in fluorination, bromination, chlorination, they are overall, the sum of this minus the sum of this will be negative, because more energy is produced than it is invested. This is negative, negative because they are formed, they are released. This is positive, positive, they are invested, absorbed. So sum total is negative for all halogenations except iodination. Now I told you why we abandon fluorination, because of its uncontrolled nature. Fluorination is dangerously explosive and difficult to control, and hence not done. Iodination does not take place photochemically. Photochemically means initiated by light, or thermally initiated by heat, as the overall process is endothermic. Not only that, the overall delta G, free energy change, is positive. This is the main criterion. As you know from thermodynamics, if delta G of a process is positive, then it's not possible, non-spontaneous. And in all other halogenation, it is negative. Now, chlorination and bromination, they are the most common among the halogenation, therefore, and that goes via free radical mechanism. Let's know what is that. As I have already told you, free radicals are reactive neutral species containing an unpaired electron. Among carbon free radicals, I can remind you the stability order. The least stable is phenyl or vinyl, having a sp hybridized carbon. And the other, among other alkyl, 1 degree alkyl is less stable than 2 degree alkyl and less stable than 3 degree alkyl free radical, because you know, due to hyperconjugation effect, more number of hyperconjugation structures, a 3 degree like third butyl free radical is much more stable. An allyl radical is stable due to resonance. So also benzyl, I have shown you here, this is phenyl, this is 1 degree, this is 2 degree, this is 3 degree, this is resonance, allyl, and this is benzyl. This is the order of stability of carbon free radicals. And you already know that for getting radicals, you need to have 1 electron shift, shown by a fish hook arrow, not by a conventional arrow mark, which is a 2-electron shift. This is a 1-electron shift shown by this kind of half arrow, or it is called fish hook arrow. And interestingly, free radical reactions are always self-sustaining chain reactions, in which a particular free radical is produced again and again, repeatedly, very fast, following the same cycle till the reaction is complete. That is why it is called chain reaction. Just like fission, in fission there is a chain reaction, it continues very fast. Similarly, here also in free radical process, may it be a substitution that we are dealing today, next time we'll be doing free radical addition. So in free radical process, it's a chain reaction because a particular radical is produced again and again following the same cycle and very fast. Now, every free radical process has 3 main steps. The first step is initiation. Just like in your school, you have your PT, physical training instructor, PTI. And when he says, on your mark, say, go, you run. So that he initiates the running process. So the free radical process is initiated by some free radical. And that is called the initiation step, the beginning. I used to call it to whistle, just like a PTI whistle. On your mark, say, it's like that. Then propagation starts. Once the PTI whistles, then he can go back to his home. Others are there to look after whether someone is coming first or second. The PTI has no role. Others can take charge. PTI simply whistles to start the propagation. Same thing happens. Let me read out. Follow me. In this step, the first few free radicals are formed. We need a few free radicals to start. Once started, no further initiation. PTI is not required. No further initiation is required. Now, in this step, homolysis of a bond of a particular reactant or a particular catalyst, what we call initiator, that is this homolysis due to the application of light, UV or visible light, or heat, or both, to produce free radicals. These are sometimes called primary free radicals because they will enter into the propagation steps. In halogenation, halogen itself, chlorine-chlorine bond or bromine-bromine bond, is broken to form 2 halogen atoms, or we can call it free radicals because it contains an unpaired electron. So, halogen molecule X2, chlorine, chlorine, bromine, bromine, this bond undergoes homolysis, shown by a fish hook arrow on both the sides, to produce 2 halogen atom, chlorine atoms or bromine atoms, what we call free radicals. And a very small amount of these halogen free radicals are required in the initiation step. Once initiated, radicals are self-generated in the propagation step. Now propagation comes. PTI has gone home. Primary radicals have come to propagate the chain. Now what happens? Alkane, any alkane represented by RH, now reacts with this halogen. For example, this is bromine free radical, bromine atom or free radical. I have taken an example, bromine, any alkane. Now this CH bond breaks homolytically. Bromine joins with hydrogen atom to form HBr, and one unpaired electron comes here to produce alkyl free radical, carbon free radical. In fact, propagation, that step is the chain part of the reaction mechanism in which the same consecutive reactions are repeated many times in a cyclic manner before the reaction stops. This cycle involves the following two substeps. Step A, the alkane, one of the CH bonds of the alkane breaks and the H dot Br dot combines to form HBr, producing an alkyl free radical. And this alkyl free radical combines with a bromine molecule, bromine or chlorine molecule, no more X dot. You will see X dot will be generated in the propagation step itself. No more initiation required. So in the second substep of propagation step B, the alkyl free radical reacts with a molecular halogen, chlorine or bromine, a diatomic halogen, to abstract a bromine atom, and this R dot combines to produce a molecule RBr, and that is the product, alkyl bromide or alkyl chloride. And another halogen radical is set free to again attack another alkane, and then it combines with this bromine which is produced in B, reacts with another alkane to produce another free radical, carbon free radical, alkyl free radical, and HBr, the other product. And this R dot combines with another molecular halogen to produce RBr, and again Br dot. So these two steps, substeps of propagation, they continue repeatedly. This is a cycle, A to B, B to A to B, until RH, almost all RH alkane is exhausted, or all bromine or chlorine is exhausted. So this takes place very fast. Now you may ask a question to me at this stage. On your behalf, I am asking a question. What? That why not this R dot combines with Br dot to produce directly the product RBr, and one H dot is set free. So we can, in one step we get RBr and H dot. No, that doesn't take place. I will answer this question just after a bit. Hold your breath. Now, I have already told all these things, so there is no need to, and I am showing you the energy profile, where this is the potential energy of the entire reaction process. This is the reaction coordinate, how the reaction proceeds with the time. Now this is the supposing methane and one chlorine radical. This chlorine radical or bromine radical formed in the initiation state. So this is the depiction of the propagation state. Initiation is over. So one chlorine radical combines with, reacts with CH4, abstract H dot to produce HCl and CH3 dot. You know, this is the radical intermediate. This is represented by a energy minimum, right? And you know, this activation energy is large. That is why this is a slower process. And then the radical, alkyl radical, combines with another molecular halogen, chlorine, Cl2, to produce finally the product CH3Cl. HCl has been already produced here in this step, and a chlorine radical which will go here and again start the same propagation cycle. So this is step A is complete here, step B is complete here. So this this is, endothermic. The first step is endothermic, this much. Endo plus 8 kilojoules. But the second step is highly exothermic, minus 109. I'm talking of chlorination. Bromination is also similar trend. Fluorination, our hands are tied. It is dangerous. Same trend. But iodination, it is the opposite, where the net process, the sum of these two in fluorination, chlorination, bromination, they are negative, minus 109. This is larger than this, but iodination is the opposite. That is why we do not have iodination possible. Not only delta is positive, but delta G also becomes positive. Therefore, and then after propagation is over, then comes this step 3. There are 3 steps. Initiation. On your mark, set, go. Then propagation. This cycle is continued. Only the reactant alkane that is consumed and other other reactant bromine or chlorine is consumed, and it goes on and on, producing free radical again and again, halogen free radical and products. Finally, the time comes when the residual free radicals, they will combine with each other. They will die out, because the free radicals are unstable species. They have to die, although they are neutral species, but they are not stable species. So they have to die out, form stable molecules. So the way they die out, that process is called termination of radicals. Step is called termination. So at the end of the reaction, the radicals can combine with each other. All types of free radicals produced. There might be some very, very trace quantities of all types of radicals which are yet to be exhausted. So they will quickly combine at some stage to stop the propagation. Propagation will not be allowed indefinitely. It has to come to an end. So that is done by the process of termination. So there are 2 ways I will tell you now. There are other ways also. The 2 ways are combination of radicals. The second one is disproportionation between the radicals. And now this termination process will produce a very small quantity of products. Some of them are invisible because they are already there. They were there. But still they will be produced in trace quantities in this step. But other products will surprise you. That how this product is formed, however in small quantity. It may be while the reactant is this, how can the product will be this? You will be astonished. But yes, it is being formed, and this is explained by free radical mechanism. Now see, one of the processes that all right types of radicals will combine. R dot and R dot will combine to produce higher alkane. Methyl to give you ethane. Ethyl to give you butane. So you have taken methane and chlorine or bromine. You are expecting methyl chloride, methyl bromide. Yes, you have got it. In the propagation step, you have definitely got it. But in the termination step, you get a trace quantity of ethane. That will surprise, and that will come as an impurity. That will be there as an impurity in the termination due to the termination step. And R dot will combine with Br dot. This is not a new one. This is invisible. You can't know because it was already there, predominantly formed as the product in the propagation step. So you can't know whether it is formed during termination or not, but it is formed. Now again, bromine dot can react with bromine dot to produce Br2. But this is also invisible because it was already there in the reactant. So this product will surprise you. Now, disproportionation between radicals occur when at least there are two carbon atoms in the radical. It cannot happen in the halogenation of methane. Only ethane and onwards, higher alkenes, they will produce some trace quantities of disproportionation products. Now see here. Now here, ethyl radical and another ethyl radical. Two ethyl radicals will exchange a hydrogen atom. For example, here is the radical site, but the other carbon, that one hydrogen atom will be abstracted by another ethyl radical. So this dot and this H dot will combine to produce CH3. So this becomes an alkane. And another dot which will come here by the homolysis. And this dot which is already there, they will unite to form a pi bond so that you get a stable alkene and alkane. So this is the disproportionation of organic species. Two ethyl radicals, they disproportionate to produce ethane and ethene. Yes, ethane can be invisible because during the reaction of ethane with bromine, ethane was a reactant. You may think some of the ethane might be left out, but this is also formed in trace quantity during termination process. But this will surprise you how ethene, a double bond, will be formed. This is a radical substitution. The substitution product would be formed, and that is formed in large quantity. But a trace quantity of ethene, that can only be possible or explained through this disproportionation radical mechanism. Now let us talk more about initiation step, which we will not discuss more here. They will be needed in free radical addition. For some cases, for example in free radical addition or even liquid phase substitution, we need the help of some other radical initiators. Chlorine, bromine, they themselves, they break down to produce radicals. But sometimes we take the help of other proven good free radical producers or initiators. And those among them, the commonest will be some peroxides, N-bromosuccinimide, famously called NBS, chlorofluorocarbons, AIBN, remember this name, azobis isobutyronitride. Don't remember this, I'm sorry. These will be discussed later. Are used to generate primary free radicals. Among peroxides, you can have hydrogen peroxide, the simplest, looking like water. Benzoyl peroxide, 6,6H5CO, this is the peroxyl linkage. Then CO, C6H5. Ditertiary butyl peroxide, DBPO. Chlorofluorocarbons can be many. Out of them, I have given one example, CF2CN2. NBS is N-bromosuccinimide. I will give you the structure later. AIBN is azobis isobutyronitride. The details to be discussed later. I have shown you when you take the help of another foreign initiator to produce primary free radicals like benzoyl peroxide. This peroxy bond, this middle bond will undergo homolytic cleavage. To produce two, this is called benzoyloxy free radical. And also after some time, there will be loss of carbon dioxide. One dot will come here, one dot will come here and form a double bond, and carbon dioxide will fly away. And then you get phenyl free radical, which is not stable. But these two types of radicals are produced from the homolysis of the benzoyl peroxide initiated by light or heat or both, usually heat. Similarly, a chlorofluorocarbon, when irradiated, will produce. You are not able to see. I will do it here for you. And this will produce now this CF dot, CF2Cl dot plus Cl dot. Still you are not able to see. Okay, then I will do one thing. I will just remove it. It is under my control. So I will show you that if you take a chlorofluorocarbon like CF2, Cl2 and put sunlight, then there will be homolytic cleavage. So you get one CF2Cl, this radical, free radical, plus one chlorine free radical. Similarly, this is called azobis isobutyrionitrile AIBN. There is an N double bond N in the middle. This is isobutyrionitrile CN, cyanide group. This is isopropyl, and this is also same. And when you hit it, then this bond breaks homolytically. One electron comes here, one electron comes here. There is a triple bond. Nitrogen flies, and leaving behind the isobutyrionitrile radical to undertake propagation. Now these are produced to undertake propagation because sometimes we cannot take chlorine bromine to take some other species which cannot produce free radicals. So the primary free radicals are provided by some known initiator. Just I'm sounding you. It will not be required in our program today. Similarly, in case of NBS, remember this, N-bromo, this is called succinimide, NBS. Now when you heat it, this bromine dot goes and this radical comes. So this is the way. And halogen bond we have already shown. So also any peroxide, may it be benzoyl or maybe anything, dot butyl or anything. So this OO bond breaks to produce the alkoxy free radicals. And let me now tell you why this doesn't happen. This does not happen. You might have asked me a question, why the free radical produced in the initiation state, that is halogen free radical, does not abstract R dot to produce directly the product and produce a hydrogen atom, a free radical. This process, the delta G is positive. And in fact, delta H is also positive and delta G is also positive. So this is thermodynamically forbidden. This delta G is highly negative, so this process occurs, this doesn't. If there are more than one non-equivalent carbon sites, now here I have written that abstraction of hydrogen by halogen radical forming HX and alkyl free radical is thermodynamically favorable, while formation of hydrogen atom and RX is forbidden. Delta G for the former process is negative. And in fact, if a particular alkane contains more than one type of carbon where substitution will occur, it has a 1 degree carbon, 2 degree, 3 degree. So there is always a preference of the radical attacking the different types of carbon atoms. And you know the order is 3 degree carbon is most reactive, followed by 3 degree carbon is most reactive, followed by 2 degree, followed by 1 degree. It is because the resulting carbon free radical will be more stable. If it is a 3 degree free radical, more stable. 2 degree, less stable, but more stable than 1 degree. 1 degree, least stable. So if you carry out a substitution, bromination of propane, the bromine radical formed in the initiation state has two possibilities. One, it will abstract a 2-degree hydrogen. This is a 2-degree carbon. This is a 2-degree carbon. Let me show you here. And these two are 1 degree, and most importantly, they are equivalent. They are equivalent. So this is 2 degree. So the preference is 2 degree over 1 degree. So this is why? Because it will be producing a more stable secondary free radical, having more number of hyperconjugation structures. There are 6 alpha hydrogen atoms. I'm just reminding you, those who have not studied hyperconjugation, never ever mind, read it. You can watch it. I have given the study materials in every video in the description box. You must follow them. And the second possibility is to abstract a hydrogen from the primary. This is 1 degree. These two are equivalent, and out of them anyone can lose a hydrogen atom to produce HBr, and you get a primary free radical which is less stable. So there will be always a preponderance, a dominance of one radical over the other, hence a major product and minor product will be always there, right? Now sometimes the radical mechanism becomes so fast, we have to control it by adding some retarders, which will slow down the reaction. Sometimes we call inhibitors. Don't be swayed away with the word inhibition. Inhibitors are not literally, in a literal sense, they are not used. Inhibitors are the substance which retards, decreases the rate of reaction. Sometimes, yes, if you take in large quantity, then the reaction may stop. In that case, a literary meaning will come, that is, inhibits the reaction. But always inhibitors, they do not mean complete end of the reaction or stopping the reaction. Addition of some substances like even oxygen gas retards or inhibits the continuation of the chain reaction. Why? By combining with the radicals, the alkyl radicals, which are produced again and again, the bromine radicals. They are captured by oxygen because oxygen itself is a diradical. It contains 2 unpaired electrons. So they capture the radicals and stop propagation cycles. Sometimes in other processes, you will know, other inhibitors can be used like hydroquinone, hydroxyamines, some phenolic compounds. We are not interested in those things now. Let us know more about termination state. That is, termination step is a thermodynamically disallowed, it is non-spontaneous, because the entropy factor is highly unfavorable. Delta S is negative because the radicals where you will combine so that the number of species making chaos becomes less. So delta S is negative, and even if delta H is negative, but due to delta S factor, delta Z becomes positive, and therefore termination step is thermodynamically unfavorable. The equilibrium constant is very low, much less than 1, but it happens. Therefore, the products formed in the termination step is very, very small, less quantity. That is good enough to provoke our excitement, to arouse our curiosity. How in the you have planted, say, some seeds like brinjal, but in that you will be harvesting some other like potato. Is it possible? So we have taken methane and you are getting ethane, those trace quantity. You have taken ethane, and as well as butane. This is incredible. That can only be explained through mechanism. Now we end the first part of this lecture. The second part will be doing this very interesting. No, don't go away. You finish this. This is Reactivity-Selectivity Principle, RSP. I used to funnily call a Raulkela steel plant. If you are an Indian, Raulkela is one of the famous steel plants controlled by SEL, Steel Authority of India, RSP, Reactivity-Selectivity Principle. That is very interesting. There will be a competition between chlorine and bromine. Who will be more popular in halogenation of alkanes? Alkenes having allylic hydrogen and arenes having all these and different examples we shall be looking at in our next video. Bye bye. Will I ask you at the end, of course, as a formality, to why formality? It's a fact to like if you have really enjoyed, and also to subscribe my channel if you are really following our videos. See you immediately after some time. I will just take a cup of my favorite lemon tea and start RSP. Bye.